Good morning. My name is PICo-satellite, and I'm currently employed as an electronic engineer and a project engineer at the Belgian Institute for Space and Aeronomy in Belgium. Today I wanted to show you a bit more about our CubeSat project PIC.A.S.O. I've subdivided my presentation into two main blocks. First of all, I want to discuss to you the generals of the project itself, and then I will go a bit more into the CubeSat itself. So this is the big picture of PIC.A.S.O. As you can see, it's a 3-unit CubeSat. We at the Belgian Institute for Space and Aeronomy, we are a scientific institute of the Belgian federal state. And currently we are, with all institutes, around 150 people, mostly scientists and engineers. The institute itself has been created in 1964, so we've just celebrated our 50th anniversary. And our main tasks are mainly scientific research and to support and to give service to the Belgian policymakers with respect to physics and chemistry of the atmosphere, of the Earth, and of course of other planet atmospheres. The scientists rely their material on ground-based air and spaceborne instruments. They will also do a lot of theoretical studies and build computer models. Important to say is that education and technology development is not a part of our main business, so we don't develop CubeSats ourselves. But of course, we've discovered that CubeSats might be a very, very interesting tool for us to show that we can build some great science by using them. So, indeed, at PICo-satellite, we believe indeed that pico and nano-satellites can give us an important role in the future to do some Earth observations. Why? Because, well, mainly because they are cheap and they can be deployed around the Earth and give us a big spatio-temporal coverage of the scientific measurements. Of course, due to the fleet redundancy, if some CubeSats fail, we still have enough data to work with. Because we could produce so much satellites, the main cost will remain low. And of course, because it's a cheap satellite, for small countries like Belgium, or even for institutes, this is very affordable. So we thought, yeah, why don't we use this to test a potential kidney scientific mission? That's we came up with PIC.A.S.O. So in PIC.A.S.O we have two main instruments. The first is called Vision, and Vision is really a near-infrared hyperspectral imager. And with Vision we would like to retrieve vertical ozone density profiles and to retrieve the temperature of the upper atmosphere by doing sun occultation measurements. Another instrument is SLP, or Sweeping Langley Probe instrument, and with that instrument we would like to measure the electron density and temperature of the plasma. So PIC.A.S.O has its internal kickoff at PIRA somewhere 3 years ago, but we can announce some breaking news today, because last week we were officially an ESA mission. Our kickoff is planned to be on the 21st of October, so within a few weeks. In this project, PISA will act as the prime and will take care of the management, the scientific aspects, and the entire development of SLP and embedded software development of the Vision instrument. We of course also have a lot of partners. We have the Centrale Spatiale de Liège, or CSL in Belgium, who will do the system engineering for us and will be doing the product assurance and quality assurance. Then the hardware development of the Vision instrument will be done by VDT of Finland. Then our main subcontractor is CubeSat. They will deliver to us the platform itself and do the development of the platform, and they will also be responsible for the payload integration. They will perform all tests that are necessary, and they will also do the ground station and the operations of the satellite. So, all in all, PIC.A.S.S.O is an end-to-end mission with an expected total duration of 29 months. Of course, we want to be launched in the frame of the QB50. Here you get an overview of all our main sponsors, the consortium, and our partners. So, in the middle, here you have ESA. You see, it's the main part is the ESA project. And we have CubeSat, VTT, and CubeSat as main subcontractors. But of course, there are a lot of sponsors, PICo, the European Space Agency, the National Rotary, STC. So there are a lot of people involved in this project. Now I came to the second part of my presentation to tell you a bit more about PIC.A.S.S.O itself. So, as I already said, PIC.A.S.S.O is a 3-unit CubeSat, where one cube is left for 2 scientific instruments. The other 2 cubes will be used to build in the flight, the flight electronics. We will have 4 2-unit deployable solar cells to produce the energy that we need. We have an altitude control system that is also built and developed by PICo-satellite. There were some main parameters we needed, and that was one of these parameters was that we needed a pointing accuracy of at least 1 degree to point at the sun. This was very important for us to take some good measurements so that the sun would be in the field of view of our sensor. For that we use 3 dynamical wheels and magnet torquers to unload the wheels if necessary. The total mass expectation is around 3.7 kilograms. The total satellite produces around 10 watt, but we would use only 6.5 watt for the entire satellite, so we still have some margin there. And to do the telecommunications, the telemetry and telecommands are done by using VHF for downlink and UHF for uplink. The data itself will be transmitted over S-band because we need a big data rate for that. We've done some estimations and we think we are roughly at 50 megabytes per day of data. So a bit more about vision. So vision is our spectral imager for occultation and night load, and it has 2 main scientific goals. The first goal is to retrieve the vertical ozone density profiles by doing sun occultation in the Chapuis band. And the second goal is to measure the temperature of the atmosphere, of the upper atmosphere, by looking at the sun flattening caused by the reflectivity of the atmosphere. The instrument itself, which is developed by VTT, is based on the PICo filter and can work into 3 modes. The detector is a commercial CMOS sensor with an RGB matrix. The camera has a field of view of 2.5 degrees, and we work in the visible and infrared range. And the instrument itself is a rebuild of the ASI sensor that is already built onto the Alto 1 CubeSat. The other instrument, SOP, stands for Sweeping Line View Probe instrument, has 4 scientific objectives. The first one is to measure the coupling of the ionosphere to the planisphere. The second one is to investigate a bit more about the superauroral ionosphere and corresponding magnetospheric features, because we are in a polar orbit that might be interesting. Also, coupled with that, we want to measure a bit more the overall structure. And of course, we can also detect the turbulence in the partially ionized ionosphere. So the instrument itself, it's 4 needle-like Langmuir probes that will so the electrical potential of the probes will be swept with periodical time, and in that we will collect particles from the plasma. So they will produce an electric current, and this current can be measured. From this current and this potential, we could subtract the local electron density and temperature, the ion density, and one interesting fact is that we can also detect the spacecraft potential with respect to the plasma. For this instrument, we will place the Langmuir probes as far away as possible from our spacecraft, and that's why we will put them on the solar panels, so they will act as booms for our probes. So if you're interested about the scientific purposes of vision in SLP, well, our posters are waiting for you in the corridor. I don't know if there are any questions left.
Thank you for the presentation. Any questions for the speaker? Oh, please.
Just a question in relation to the total duration, 29 months.
Yes.
It starts from the production, I mean, implementation of the satellites, or starting with the 21st of October?
Officially starting from the 21st of October, but because we are already 3 years in progress, a lot has been done in kind, as an in-kind contribution in PICa itself. So you could take.
But 29 months, it's more than 2 years. What
Yes.
orbit you will use for such a project?
Normally we will be in a polar orbit with 98 degrees of inclination. For the moment we have found a launcher which would bring us in an elliptical orbit between 380 to 700 kilometers. So that's roughly the 500 kilometers we would need to do these experiments. But because we want to be in the launch of the QE50 framework, we have set the launch date up to the beginning of 2016.
But do you have the possibility to correct your orbit during the after that launch?
No, so the satellite doesn't carry any propulsion system. The only thing we can do is to stabilize the satellite by these flight wheels and microtorpors.
Okay, thank you. Any other question? Matt, please.
I mean, just using one ground station?
For the moment, we are just using one ground station, the ground station that FlightSpace will provide us. But the possibility is still open to also use, for example, the RE2 ground stations in Luxembourg. Because we are now in the PICa framework, this possibility is still there.
Any other questions? Again, I have one myself.
Yes.
As your CubeSat will fly and your Langmuir probe is sensible to electrons, how are you going to equalize the potential of the CubeSats?
Yeah, that was one of our biggest problems we had. So we cannot do long measurements because we would collect too much particles and our measurements would be totally wrong. We came up with a quite clever solution for that, and that's we decouple our entire instrument from the spacecraft and measure in floating mode. And by doing very, very short and fast measurements, we collect just as much particles as we need to do the measurement. And afterwards, we connect back our instrument to the spacecraft to level again the potential and to transmit the particles back to the plasma by using conductive surfaces on the satellite.
Okay, thank you. Thank you again for the presentation.